On May 18, 1980, a catastrophic geologic event occurred that not only shocked the world because of its explosive power, but it challenged the way we think about how the Earth formed at its very foundation. That event was the eruption of Mount St. Helens here in Washington State in 1980. I believe that the eruption of Mount St. Helens is the geologic event of the 20th century. Come with me and relive the volcanic eruption of over 30 years ago. Take a look at what the volcano did in very short order. Then apply what we have seen at Mount St. Helens to other geologic features of the Earth and experience the rapid regrowth of the plants and animals on this landscape. And then finally, think about the implications of what Mount St. Helens says to you and me personally about ourselves, what it says to us about the Earth, and ultimately what the volcano says to us about God. On May 18, 1980, at 8:32 a.m., a report was radioed from this ridge back to Vancouver, Washington. The report was, Vancouver, Vancouver, this is it. And Mount St. Helens exploded. It was a pristine mountain with a very beautiful virgin forest. The volcano was 9,677 feet tall before the eruption. All that changed as it lost 1,300 feet of summit elevation on the morning of May 18th. 1/2 cubic mile of summit slid away and a Richter magnitude 5.1 earthquake. As the summit slid away, the steam pressure inside the volcano was released. This explosion was directed northward over the landscape and leveled 150 square miles of forest. It included this ridge where I'm standing on. Then behind that steam blast was that debris avalanche, the rock fall that was caused by the earthquake. It formed a giant debris stream that covered 25 square miles. This debris avalanche was a slurry of rock particles and gas that overtopped these ridges and caused enormous damage. 3/8 of a cubic mile of the landslide material, about 3/4 of the landslide, went over this ridge here at Johnston Ridge and down into the North Fork of the Toutle River Basin. And about 1/4 of the landslide material, the debris avalanche, entered the Spirit Lake Basin. The landslide barreled into the lake and caused a giant water wave, 860 feet high. The lake was washed up on the north shore of the lake. That water wave washed the logs back into the lake, creating 1 million floating logs. And the lake sloshed back into its new basin with a landslide debris dam at its corner more than 200 feet higher than the pre-eruption level. Then the North Fork of the Toutle River below me here, this basin was changed by pyroclastic flows moving at twice freeway speed. These hot glowing avalanches of volcanic debris came as a giant avalanche down into the landslide debris that was blocking the valley. And then we had all the melted ice and snow around the volcano, and that formed these mud flows. The mud flows were very significant. On 6 major rivers downstream, dozens of bridges were washed away, and logging camps were overcome, and houses were washed away, and it killed 57 people. The volcanic explosion rained particles all over the landscape, and we had this airfall tephra. This 25 square miles of landslide debris is Earth's newest landscape, and we need to look at it to see all the lessons that it can teach us. Mount St. Helens was just a small to average volcano from the standpoint of human experience and history. There've been a lot bigger volcanic eruptions. That day on May 18th, the volcano released the energy equivalent of 440 million tons of TNT blast energy. That's equivalent to 33,000 Hiroshima-sized atomic bombs. That's an atomic bomb a second for 9 hours. So during the 9-hour eruption on May 18th, we see the power output of about an atomic bomb a second. Yet there are a lot bigger volcanoes from the standpoint of human experience in history. Yellowstone exploded more than 2,500 times the explosion power of Mount St. Helens. The giant Yellowstone Lake Basin was created by the collapse of that super volcano. Mount St. Helens just a small to average volcano, and we see huge volcanoes in history. We're here in the landslide debris deposit north of the volcano on the channel of the North Fork of the Toutle River. We see erosion and the effects of erosion here, but the most important thing to see here is the sequence of strata that have formed. Since 1980, in this area, up to 600 feet of deposits have occurred. We have eyewitness reports and photographic documentation that allow us to piece together the sequence of the deposition of these deposits. The 600 feet of deposits has a story to tell. Each layer has a date, and we can understand how strata form here. This is one of the most amazing features of Mount St. Helens, is the rapidly formed strata layers. We see right behind me here the base of this cliff, the lower half of the cliff, is composed of the airfall deposits, the airfall tephra from May 18, 1980. During the afternoon of May 18, 1980, the volcano was quieting down and airfall debris, large blocks of pumice and fine ash, fell on this surface. Then up above it, we see a 25-foot thick layer of layered volcanic ash. That's the pyroclastic flow deposit from June 12, 1980. And then on top of that, we see the mud flow from March 19, 1982. Each layer here on this cliff has a date, and we can establish the sequence of the formation. One of the most interesting things about that June 12, 1980 pumice flow deposit is it formed essentially in 3 hours. We have the radar imagery that shows between 9 p.m. and midnight on June 12, 1980, that a big plume of volcanic ash was forming over the crater of the volcano, and these slurry flows came down and deposited the pyroclastic flow deposit of June 12, 1980. The most amazing thing about that is its layering. Then above it is the mud flow deposit, March 19, 1982. Every layer has a date, and we can understand the process of the deposition of these layers by looking in detail at these strata. We're here at this cliff on the North Fork of the Toutle River, which shows the very beautifully preserved pyroclastic flow deposits from June 12, 1980. Late in the evening, about 9 p.m. to midnight, this deposit was formed rapidly during 3 hours. You can see the effect of the pyroclastic flows. The coarse and the fine material is separated into thin layers called laminae. And the laminated appearance of the pyroclastic flow deposits is really interesting because it shows us that particles can be separated at high speed. These pyroclastic flows were moving at about 100 miles per hour. As the grains were being propelled over the surface in a slurry, the particles separated, coarse and fine, into thin layers. I had thought that a catastrophe would mix up all the particles and make a homogenized deposit. Boy, was I wrong. Right here, a pyroclastic flow moving at freeway speed or higher can separate particles into coarse and fine. So layering doesn't require millions of years, thousands of years, or even hundreds of years. It can form rapidly in this slurry flow process. So Mount St. Helens tells us something really interesting about how rapidly strata can form. There's even micro-thin lamination in this deposit. It's remarkable. These strata that we see here at Mount St. Helens that formed rapidly help us understand the sandstone strata that we see in Grand Canyon. For example, many of the sandstone strata in the bottom of Grand Canyon have the layered appearance and some of the same structure as we see here. I had been accustomed to thinking of Grand Canyon strata forming over millions of years. I was taught that at university. But the process can form the strata very rapidly. We don't need millions of years to interpret strata layering, and what we see at Mount St. Helens helps us understand Grand Canyon sandstone strata and other strata that we see in Grand Canyon. So Mount St. Helens provides a miniature laboratory for the study of particle stratification. We're here on the north flank of Mount St. Helens in the basin called the North Fork of the Toutle River. This is the site of the enormous debris avalanche deposit. This deposit is sitting over about 25 square miles, and it makes this enormous area that's Earth's newest landscape. Before the eruption, this was sky. Now it is landscape. And so everything we see here is formed since 1980. What is interesting is that canyon up there called Lewitt Canyon on the left. Lewitt Canyon on the left is eroded over 100 feet deep through solid rock. There's a 500-year-old lava flow that's been gouged out by the force of mud after the summer of 1980. The right canyon over there is even deeper. It's called Step Canyon, and it's eroded over 600 feet deep through lava flows and volcanic ash deposits. All of that erosion occurred rapidly after the summer of 1980. Now we're down here in the landslide deposit. This whole landscape here has been radically altered by the forces of erosion. Here we see this giant terrain which had originally a pit, a low area here, and then on the downstream side there was a debris dam of landslide deposit across that valley. This whole valley was filled with mud up to a level of about 125 feet across the valley. Then the mud overtopped this debris dam and cut down and made a whole series of canyons. We're on the North Fork of the Toutle River, upstream in the landslide debris deposit area where the canyon has been cut through. You see this deep canyon over 140 feet deep, eroded through the deposits since 1980. It might appear that this river eroded this canyon one sand grain at a time over maybe thousands of years, but it didn't happen that way at all. We know from the historic reports and the photographic documentation that this canyon was breached in a single day by the mud flow of March 19th, 1982. There was a giant debris dam here where mud spilled up against it, overtopped the dam, and the downroding mud made this canyon. The stream is caught in this canyon. The stream does not cause the canyon causes the stream. We're looking here at some really remarkable erosion, and all over the terrain and the landscape north of the crater at Mount St. Helens, we see these kind of features. Rapidly formed canyons, having the appearance of maybe thousands and thousands of years, but we know that they formed rapidly. In 1983, we called this the Little Grand Canyon of the North Fork of the Toutle River. And it's a 1/40th scale model of Grand Canyon. Of course, it didn't take millions of years to form this canyon. This was formed in a day by the power of mud that breached that giant debris dam and cut back through this pit. So this terrain is not slowly evolving. It has been formed rapidly by catastrophic process. Most people have heard the theory that the Colorado River has been flowing through the canyon, eroding it very slowly over the period of tens of millions of years. That theory has been popular, but most geologists now have junked that theory and are going to a different theory to explain the origin of Grand Canyon. There are many theories out there for how Grand Canyon was eroded, but most geologists are dissatisfied with the idea of the millions of years river. Geologists are speculating that Grand Canyon formed rapidly. There are various ways that it may have formed. The one I like is the idea that there was a great lake of water upstream from the Grand Canyon in the Hopi Desert area, and this lake drained through the plateau in northern Arizona. It breached a dam and drained through the area of the Grand Canyon, 270 miles long, an enormous spillway and drainage of lakes to the east and to the north. Grand Canyon may be explained by catastrophic process, and Mount St. Helens, with the breached dam and the mud flow that occurred, might be a good example. Grand Canyon could be a gigantic breached dam formed by rapid drainage of water from lakes. And it's illustrated by the landscape here at Mount St. Helens. We see at Mount St. Helens the landslide debris that was blocking the valley and the mud that overtopped and breached a dam, creating a spillway with a whole new series of canyons, even a miniature Grand Canyon. So Mount St. Helens provides a model for how Grand Canyon was eroded. On May 18, 1980, when the volcano exploded, there was this gigantic landslide, the largest landslide in recorded history. This lake was displaced by the landslide. As the landslide barreled into the Spirit Lake here, it propelled the water of the lake up to 860 feet above the pre-eruption level. The landslide debris deposited an average of about 200 feet of rock material on the bottom of the lake, and the lake was up high. As the water spilled back into the basin from the gigantic water wave, it brought in all these logs. The day after May 18th, 1 million logs floated on Spirit Lake, and geologists had the opportunity here to study how logs would float over the years as the lake was recovering from the eruption. These logs that float upright in Spirit Lake are amazing. I had to study these logs. One way we could study the logs is by sonar survey. And we brought a sonar device into the lake. In a boat, we brought automobile batteries, a sonar recorder, and we towed the sonar towfish under the boat and did the sonar survey of the lake. We found hundreds of upright objects standing on the bottom of the lake. They cast their sonar shadows over the bottom. And you can see the bottom of the lake about 50 feet below the towfish, and you see the image looking out over the side of the boat about 50 yards. And we see 3 upright floating and deposited logs on the bottom of the lake, thin pencil-like reflectors that's standing up off the bottom. This one image here shows what appears to be an immense sonar reflector standing off the bottom of the lake, casting an immense shadow. It even seems to look like a base of a trunk of a tree without flaring root mass. As we did the sonar survey of the bottom of Spirit Lake, we discovered hundreds of upright objects, over the small area that we studied, and we estimate that something like 10,000 logs were standing upright on the bottom of Spirit Lake. We had to go diving in Spirit Lake to see what the bottom of the lake was like. We went with the scientific diving equipment with cameras and submerged ourselves in the lake. On the bottom of the lake, right where the sonar said they would be, we found upright deposited logs. These logs even have outflaring root mass, often broken near the base of the trunk of the tree. Some of these logs are solidly embedded in the bottom of the lake. Others were easily tipped and swayed. That proves that the logs fall out at different times on the bottom of the lake. And they have their root ends planted at different levels, having the appearance of being multiple forests. All of this happened very recently here at the volcano. These logs floated on the lake, they floated upright, fell to the bottom, got replanted in different layers. We even studied the species of logs as they floated. For example, some of the logs continued to float very well, the Douglas fir trees, whereas the noble fir and the silver fir trees, they fell out very quickly. So we have a species stratified deposit in different layers, upright logs, having appearance of being multiple forests. What we saw on the bottom of Spirit Lake was remarkable, and it needed to be applied to other things that we see in the earth. What would Spirit Lake look like if you drained it? It would look like a forest that was replanted. It didn't grow there, but it's replanted. What we have seen is the first step for the formation of petrified forests right here in the bottom of Spirit Lake. Could what we have seen here in the floating logs at Spirit Lake, could that help interpret the petrified forests of Yellowstone National Park? Here we see the sign that existed for many years at Yellowstone National Park. The sign says, "Across the valley rise the slopes of Specimen Ridge, but the forest you see there today is only the latest chapter in a remarkable story. Buried within the volcanic rocks that compose the mountain are 27 distinct petrified forests." And the right side of the sign there at Yellowstone National Park says, "Yellowstone's fossil forests are unique. Many stumps stand upright in the same sites where they grew millions of years ago." The sign talks about millions of years and enormous periods of time. Take a look at the petrified logs. They're standing vertical out of the deposit here. These are very beautifully agatized trunks of trees. And what more natural interpretation than to say, here is the modern forest growing there today, here is the ancient forest or series of forests that grew millions of years ago. We were able to dig out the roots and the bases of many of these logs. We discovered something. The roots did not taper to a point. They often terminate abruptly about 4 feet from the base of the trunk of the tree. And we found no soil horizon for these logs that are buried beautifully agatized at Yellowstone National Park. That would seem to prove that they did not grow in place. We studied the logs at different levels at Yellowstone, and we found a correlating tree ring sequence proving that logs with their root ends buried at different levels grew at the same time, thereby falsifying the petrified forest interpretation of Yellowstone. What we see here at Spirit Lake helps us interpret the log deposits and the petrified logs that are buried in the earth. The process that's going on here at Spirit Lake of flotation, upright deposition of logs on the bottom of the lake, and the burial has tremendous application at Yellowstone National Park, the petrified forest at Specimen Ridge. We see here a miniature laboratory for the scientific study of the way logs get buried, and a modern example to help us understand the rapid formation of petrified logs like in Yellowstone National Park. We're out out here amongst the floating logs in Spirit Lake, and we're out here to ask a really important question. How does coal form? You know, coal is that hard, black, compact rock that's formed from the woody tissue of ancient plants. Here we see a block of coal, and we can see the layers, very beautiful glassy layers inside of the coal block. And in coal, we see these glassy layers that are evidently sheets of bark that make the dominant structure of coal. And we look at modern swamp deposits, and we've been told that coal forms over long periods of time in big freshwater swamps. As the swamp condition prevails, the logs fall in from the forest and they get buried in the antiseptic waters of the swamp, and over long periods of time, a thick spongy layer of broken plant material called peat builds up. And this peat later gets buried by other sediment, such as clay and mud and sand. And the burial of this broken plant material is thought to have formed coal. But it takes thousands of years to form peat in swamps. Over great periods of time, it is imagined. And so a thick coal bed might be imagined to require hundreds of thousands of years to form. But can we see anything here at Spirit Lake that helps us understand the origin of coal? Along the coast of Nova Scotia, we see peat, which is accumulated over hundreds of years. The black coffee grounds to mashed potato texture peat was exposed by erosion, coastal erosion along the coast of Nova Scotia. This peat deposit shows something very interesting. Modern swamp peats are intensely root penetrated and create this homogeneous texture intruded by roots. Whereas the coal beds that we've studied show big sheets of tree bark making the dominant structure of coal. The day before Christmas, 1978, I was taking a bath, contemplating soap suds in the bathtub, and I was imagining logs rubbing against one another in a giant log mat to make a deposit underwater of broken plant material. That was the floating mat model for the origin of coal. What I call the floating mat model for the origin of coal was devised for a coal bed I was studying in Kentucky. This coal bed had layers and sheets of tree bark very obvious in it. It didn't look like the root-penetrated swamp deposit. This peat layer and the understanding of modern coal beds led me to propose the floating log mat model for the origin of coal. It was an abstract model that I was proposing. On the basis of some bathtub modeling, I was thinking about logs floating in an ocean. I defended my PhD dissertation at Pennsylvania State University on the floating log mat model for a coal bed in western Kentucky. Then, 10 months later, Mount St. Helens exploded and converted Spirit Lake into a gigantic bathtub covered with logs. 1 million logs floated here on Spirit Lake, and I had to come study what these logs were doing. Notice something about the logs here in the lake. They're floating here, but there's no bark. The conifer trees that provide the floating logs here, the bark has been removed. Where did the bark go? That's a good question. Using diving techniques, scuba investigation, we were able to sample the bottom of the lake. We found great sheets of tree bark in a thick spongy layer of peat. The bark has sunk to the bottom while the logs have floated, and it's created this very unusual condition on the bottom of the lake. The accumulation of a 3-foot layer of peat, broken plant material we call peat. If we could have ongoing burial and sedimentary accumulation, we would make a new coal bed here in the bottom of the lake. So at Mount St. Helens, we may have seen the first step for the formation of a coal bed. Does it take millions of years to form coal beds? Here at Mount St. Helens, we understand how plant material can be deposited rapidly. It doesn't take 1,000 years to form an inch of coal. The plant material can accumulate rapidly underneath these floating log mats, and you can make very thick peat deposits rapidly. And if there was ongoing catastrophic process to bury the bottom of the lake, we have all that is needed to make coal. So Mount St. Helens provides this amazing laboratory for the study of the process of coal formation. We're here on this landslide deposit, which is covered by sterile volcanic ash 30 years ago. Look at the remarkable biological recovery that's occurred here. The blue plants, lupin, fixed nitrogen and made a soil. Quickly, the Indian paintbrush and the fireweed were back in, and then the alder groves have formed. And we even see here the seedling conifers back. So it won't take hundreds of years for this habitat to recover. It's already recovered in 30 years. Large parts of the blast zone were knocked down by the steam blast, and the soil there was churned up by pocket gopher that survived. And those pocket gophers single-handedly reseeded the blast zone. And animals invaded the landscape. The elk have taken advantage of this amazing habitat, and there are more elk per square mile here than there are in the forest. The remarkable recovery here at Mount St. Helens reminds me of what it must have been like after the global flood. What is the lesson to be learned here at this volcano? Does the volcano have anything to say to us personally about our view of ourselves? Does the volcano tell us about the formation of the earth? What does the volcano tell us about God? The humanist, the person who believes that he is the master of his own destiny and control of everything around him, the humanist is humbled because here is power none under man's control. Someone else is in control. The Bible tells us who's in control. God is in control. Psalm 104, verse 32, he touches the mountains and they smoke. God reached down with his little finger and touched Mount St. Helens, and there was 440 million tons of TNT blast energy in his little finger. Although 57 people died here in the explosion of Mount St. Helens on May 18, 1980, all were warned. That reminds me that a warning has gone out through the whole world. God has provided a warning. No one needs to perish. God is not willing that any should perish, but that all should come to repentance. We see the meekness of God in giving the warning here at the volcano. At the volcano, I also think about my ordinary way of thinking. If you would have come to me before the volcano exploded and said, the volcano's gonna make thin strata layers rapidly, even in a hurricane-like flow, I would have said, no, that's probably not the way stratification is going to form. Or if you would have come to me before the volcano explodes and said the volcano is going to cause erosion by mud flows and other energetic process to create a miniature Grand Canyon 1/40th scale, I would have thought you were visionary. Or if you would have come to me before the eruption and said Mount St. Helens is going to explode and cause logs to float vertically in Spirit Lake and have them embed in the bottom of the lake, having the appearance of being multiple forests that flourished over millions of years, I would have thought you were visionary. About the only thing I might have agreed with you before the eruption is the idea that coal could be deposited underneath floating log mats. On the basis of some abstract modeling, I was thinking that way. What did I learn at the volcano? I learned that God specializes in doing things that I think are impossible. How about you? Do you have something in your life that you think is impossible? Right here at the volcano, we have a challenge to believe God for the impossible. This volcano is an extraordinary event of the 20th century. We've relived the volcanic events of 1980. We have seen what the volcano did in very short order, and we have come to appreciate the implications of those things to other geologic features of the Earth. And finally, we've asked the big questions, what the volcano says to us individually and personally, and about our view of ourselves and the Earth around us. I believe that the eruption of Mount St. Helens is the most significant geologic learning experience of the 20th century. Now that we're looking back, we can see this laboratory for the study of catastrophic process and a scale model for us to study creation and the global flood.